In the second segment of our Lahar study, we want to look about how we can actually talk about the slope of the volcano. If we look at this picture of Mount Rainier, we can see that it's got a characteristic shape to it, the shape that we expect of most volcanoes. They tend to be steep at the top and then get progressively flatter as we go off the flanks. And we see this theme no matter what side of the volcano we look at. It's steeper at the top and flatter down at the bottom. So we want to take that into account and see if we can use that to come up with a mathematically simple way of describing our volcano shape that will make the math that we need to do to solve for the Lahar problem a little bit more straightforward. So to do that, we're going to look at what people have done in the past in terms of the characteristic shape of volcanoes and how we can use those equations to then say something about the rates and timing of the Lahar. So with that in mind, we're going to look at the equations, and remember, like we showed before, we tend to think of the shape of a volcano as being steep at the top and then get flatter. So it's steep and flat. And so we can think of that by describing what the slope. Now, the actual one volcano might be a little narrower, a little wider, but in all cases we have this characteristic change from it being steep near the top and flat near the bottom. So if we were going to plot a typical volcano on the side, we would have, and we can plot, say, the slope. So rather than just draw the picture of it, the slope, and remember the slope is this part here. It's saying, what is how rapidly does it come down, and we'll talk about that in a second. But if we made a plot of the slope versus the distance from the top, we might have a plot that looks something like this. The slope is higher near the top and it's lower near the bottom. And so, at the very top it might get to be very steep, cliffs, and as we get out into the area away from that, it would become flatter. And so the question is, can we use this characteristic shape that most volcanoes have to make the solving for the Lahar behavior a little easier? And in fact, people have come up with a way to do that, and the equation that they've used is they've said that the slope is equal to a constant p times the distance down the volcano raised to the power r, or in this case minus r. And so that basically says that as x gets bigger, since this is a minus sign, this quantity on this side will get smaller and the slope will get smaller. So as we move from the top of the volcano down, we're going to get a slope that is largest at the top and smallest at the bottom. So we can use that, and if we can determine the slope, say, of Mount Rainier as a function of position, we can then solve for these parameters r and p. But it's difficult to do that, right? I mean, this is a curved thing. How are we going to come up with this? And even your Excel spreadsheet might not do that simply. So what we're going to do is take a couple of advantages of this and work with this equation and figure out how to make the slope as a function of x a function that we can easily use elsewhere. So with that assumption that we have the slope is equal to p x to the minus r, we need to essentially figure out the values of r and p, and those values of p and r are essentially just the description of any particular volcano. So different volcanoes will have different values of p and r, but they will all fit this basic equation, which is given as equation 4 on the handouts. So we want to find p and r. That's our job. We can measure s as a function of x, that is, we can work our way down the mountain, and so we can then determine s and x, and from that we'll want to solve for p and r. Now we look at this and, like I said, it's complicated. How do we fit a curve to this? But we can also look and said, perhaps if we use some other math, we can make life simpler, and in particular we're going to use logarithms to see what's going on. And in particular, we're going to use the natural log, which is written ln. We could do it with any log, but this is the way people have traditionally done this. So what we see is if we take this equation and now use a logarithm on each side of it, we have the log of s is equal to the log of px to the minus r. Now, one of the rules of logarithms is that when you have a product, that becomes an addition or a sum. So this becomes the natural log of s is equal to the natural log of p plus the natural log of x to the minus r. And a further one of the rules of logarithms says that if you have something raised to a power, the power comes outside the logarithm. So then we can rewrite this as the natural log of s equals the natural log of p plus minus r times the natural log of x. So this now makes things a little easier because our measurements, what we can measure, are s and x, but now the p and the r are outside it, and it perhaps can be a little simpler. And to do this, we can take advantage of some other things. Now I'm going to rewrite this in a slightly different form. I'm just going to move some terms around, and I'm going to write this as the natural log of s equals minus r natural log of x plus natural log of p. My reason for doing that is simply that it will now look a little more straightforward to us, because if we remember that the equation of a straight line is simply y equals mx plus b. Well, what are we looking at here? Y equals mx plus b, that's the equation of a straight line. Natural log of s equals minus r natural log of x plus natural log of p. I can make some correspondence. I can say that y is the same as natural log of s. I can say that m is the same as minus r. And I can say that x is equal to the natural log of x, and b is equal to the natural log of p. So I can relate our standard equation for a straight line to this equation we have here. So essentially we now have an equation of a straight line that if we plotted this equation with the appropriate axes, it would look as a straight line. So for example, I can take this equation, natural log of s equals minus r natural log of x plus natural log of p. And what would that look like on a graph? Well, if I make a graph, I call this axis natural log of s. That would be the same as what normally would be our y-axis. And this, the natural log of x. Then we would have a line like this. The slope of the line. Now remember, this slope is the slope of this line on the graph. It's not the same as the slope s here. This is the slope on the mountain. But the slope of this line will equal minus r. The intercept is natural log of p. So if we continue this up, we would get an intercept here, which would be natural log of p. And so we now have the equation of a straight line. So what all we need to do then is to measure x and s on the volcano itself, take logarithms and make a plot like this, fit a straight line to it, and solve for the intercept and the slope. And then we will be able to use our equation that says that s equals p x to the minus r. And that then can be plugged into the equations. So in the next segment, we will actually apply this approach of measuring x, measuring s, and then coming up with the data that would go into our natural log of x versus natural log of s plot, and then we can fit a line to it.